Hello, I am Mr. Marseille from Outward Academy Acklam. In this lesson in the Wave series, we're going to be looking at ultrasound waves and how they can be used for detection. Now, this is a triple only content, so let's get straight into it. Before we start the lesson, we just need to make sure that we have done a couple of things. So make sure your phones are on silent so that you aren't getting any notifications during the lesson that will distract you. Make sure you've got a pen or paper, or ideally some kind of exercise book so you can keep all of your notes together. Make sure you've got a scientific calculator. If you haven't got one at home, then you can download one for free from the App Store. And make sure you've got a red pen so that you can check and correct your answers. So this lesson, we are aiming to describe what an ultrasound is and what it can be used for. By describe, what I mean is you need to be able to talk about it fluently in a sentence. And the aspire is that you need to be able to calculate, so do some kind of maths, the distance to an unseen object using oscilloscope traces. Now, an oscilloscope is just a piece of equipment that converts the sound waves to a wave that can be displayed on a screen, normally to look like a transverse wave, so that you can interpret it and you can use that information and you can calculate things. With every lesson, I like to start with a recall task. The recall task is just about looking back in your memory and seeing things that we've either done in the last couple of lessons or that you've done previously in this topic, recalling them and strengthening those associations, because that means that there's more chance that you're going to be able to recall that information again in the future. So I'm going to give you 5 minutes. I'd like you to make a note of these in your book, write in full sentences. So the first question, your sentence starter is, your sentence should say the audible range of human hearing is, and then you just write the numbers. Okay. The stretch question, the purple box at the bottom, you've seen before on one of my videos. And that's because I just want to see if you can do that any better this time. So by doing things multiple times, the whole point is that we improve. So I'm giving you that chance to see if you can improve upon what you did last time. Okay, you've got about 4.5 minutes left. Okay, there's about 3 minutes left. I thought I'd give you a couple of clues for the number 2. So number 2, the part of the ear that is stimulated by vibrations within the audible range, that piece of the ear begins with C. Okay, so that might help you. For number 3, the equation that you're going to need is speed equals distance divided by time. And that's as much as I'm going to give you for the moment. Okay, there's about just under 2 minutes left. So if you're on number 4, You'll have done this during the practical where you did about reflection. So the relationship between the angle of incidence and the angle of reflection. What that means is when you drew the line going into a mirror, that's the angle of, sorry, the line going in is called the incident ray. Then you draw a dotted line at the normal, which is 90 degrees to the surface. So the angle between the normal and the incident is called the incident angle, or the angle of incidence. And then the reflecting that comes off is the reflected ray. So the angle between the normal and the reflection is the angle of reflection. So what is the relationship between those two? For number 5, state the 7 electromagnetic waves. I use a memory aid to allow me to do this. I remember that rich men in Vegas use X-ray glasses, and that helps me to remember that. You've got about 30 seconds. Okay, finish the one that you're doing, and you need to get your red pen ready to check and correct your work. Okay, with red pens at the ready, just have a look at those and check your answers. Any that you didn't get, I'd like you to cross them out and correct them, please. Just want to bring your attention to number 4, and you can see that I've put the diagram in there to show you that the angle of reflection and the angle of incidence are equal. Okay, let's look at the stretch activity. Okay, compare your labeled transverse and longitudinal waves to the one that I've got on the screen at the moment. Add in anything that you have missed. Okay, let's introduce ultrasound and see what ultrasounds are. So, I want you to just read that sentence that I've just put up on the board there. Should have said paragraph. Okay, so I'll just summarize that. An ultrasound is any sound that has a frequency above 20,000 hertz. Okay, if you look at the diagram, the range of human hearing, 20 to 20,000 hertz. So any sound above that we call ultrasound. Some animals can hear in those frequencies, but we as humans cannot. And ultrasounds have loads and loads of different uses. We can use ultrasounds to clean objects. You get toothbrushes which have got ultrasound technology, and they just means that the oscillations oscillating that many times per second that they remove the plaque for your teeth. It just basically shakes it out. You can clean jewelry, all kinds of things with ultrasound. They can be used to break down kidney stones. Kidney stones are these large masses that form in the kidneys, and they have to be pushed out as you urinate, and that can be really, really painful. So you can attack them with ultrasounds, and the ultrasound vibrates the mass and it breaks it up into smaller pieces, so it's much less painful to deal with. And the last thing, as you can see on the picture there, ultrasounds, is that we can use them to form images of objects that we cannot see. And that's what we're going to be focusing on in this lesson. Okay, so now we know a little bit about ultrasound. Let's do something with that information. So in this table that I've got here, I've got questions A, B, C, D, E, F, G, H, and a stretch question I. So I want you to get a piece of paper or your book if you're super organized, and you're going to answer those questions. Now, all of those questions, well, most of those questions, definitely A to D, and E, A, B, C, D, and E are all to do with the table that is shown in that table. So it's the one that says name of the mammal: bat, dog, dolphin, elephant, human, tiger, and then it shows you the frequencies that they can hear. So have a go at answering those questions. I'm going to give you 5 minutes. I will pop back partway through with a little bit of help for some of the earlier questions. There are some stretch questions in there as well. Don't do those initially. Do those if you still have time once the 5 minutes has ended. So I'm starting the timer now. Okay, so you've got about 3 minutes left. Let's look at part A. So A says, which mammal in the table can hear the highest frequency? So highest frequency would just be the biggest number with hertz next to it. All right, you might have to do some conversion because the highest numbers are going to be kilohertz. For part B, which mammal in the table, apart from humans, cannot hear ultrasound? So remember, ultrasound is anything above 20,000 hertz. So try and find a mammal that cannot hear sounds above 20,000 hertz. For part C, what is the name for the range of frequencies that an animal can hear? Well, that is going back to the lesson that we did on sound and hearing. So that's a little bit of recall for you there. I have mentioned it in the starter. Part D, give one example of a frequency that a dog could hear but a tiger could not. You just need to look at the frequencies in their hearing ranges and just pick any frequency that the dog can hear but the tiger wouldn't be able to. Okay, you have got about 3 minutes left, so I'm gonna stop talking and let you have some silence. Okay, you've got about 1.5 to 2 minutes left. So, part E, which mammal in the table has the lowest auditory range? Again, just looking to find out which one can, by range, remember, we mean the difference. So you're just going to have to calculate some ranges and see which one is the lowest. F, ultrasound waves, longitudinal or transverse. Again, we talked about that when we were doing the sound and hearing lesson, but an ultrasound is a sound wave. So if you know which one the sound wave is, then ultrasound is the same. G, which mammal in the table has the highest auditory range? Again, you're going to have to calculate some ranges and see which one is the biggest range. Remember, range means difference. And for this stretch, if you could tell me that range, that would be even better. H, are ultrasounds mechanical or electromagnetic? Well, you just need to remember what the definition of that. Again, it's the same as what a sound wave would be. So we did that in the sound and hearing lesson. And the Question I, the stretch question at the end, calculate the wavelength of an ultrasound wave with a frequency at the maximum that a tiger could detect. So look at the top range of the tiger and use that as your frequency. And the speed, remember, is 330 meters per second for any sound wave. Okay, that is the end of this activity. So get your red pens ready, finish off the question that you're on, and we're going to go into the next part. Okay, let's check our answers. So you can just pause the video here and you can just check your answers, match up with the ones that you've got. I will just give you, before you do that, a pointer on E and on G, because a really common misconception there would be to do 10,000 on E minus 5,000. But that is not what you should be doing. It's 10,000 minus 5, okay? And the same with G. So just check that very carefully. Let's look at how to solve the stretch question. So you needed to use the ultrasound frequency for the tiger from the table, and you needed to know that the speed of sound was 330 meters per second. So ideally you remembered that from last lesson. Bit of an exam tip here. If you didn't know that, you would have just put in any number, and as long as your working out is correct, you will still get some marks for the question. So don't leave it
how we calculate
and don't throw away all of those marks just because you don't know one part of it. Because if you, as I say, if you use a number and everything else is correct, you can only be penalised for that one part that you did incorrectly.
Frequency at the maximum
This is how we solve the full thing.
So, frequency, if we look at the table, the maximum that a tiger can detect is 50 kilohertz. Okay, kilohertz are not our international unit, our standard unit. So we're going to change that to 50,000 because kilo means thousands. We've got 50,000 hertz. Let's cross that out so we don't accidentally use it. It's an ultrasound wave. So ultrasound waves in air travel at, it's a sound wave. So if we go back to our earlier question, we know that the speed of sound in air is 330 meters per second, so we can use that. It's unlikely you would be able to to remember that number, but you could quite easily be asked to use it if you've been told it earlier at some point, or you've calculated it earlier at some point. So that's why we're doing that in this lesson. So again, we've got frequency, we've got velocity, we're trying to find a wavelength. Write down the formula that links them. Frequency, velocity and wavelength are all linked by the wave equation. V equals frequency times by the wavelength. The velocity, 330, equals sine, follow it down, frequency, follow it down, 50,000 hertz multiplied by whatever the wavelength is that we don't know. So we are going to have to rearrange because the wavelength, what we want, is on the side of the equal sign with another operation. So we have to get rid of that. So we're going to take this multiplied by 50,000 and get it over there. So we're going to do the inverse to take it over to that side. So the inverse of a multiply is a divide, and we divide by 50,000. And we do the same on this side, divide by 50,000. Okay, let's simplify what we've got. So we're left with 330 divided by 50,000 equals 50,000 divided by 50,000. Again, that's 1, so we don't need to actually write anything because 1 times by the wavelength is just the wavelength. So that's going to give us the wavelength. So now we can calculate it. So 330 over 50,000 equals SD. So we've got a number here in standard form. We've got 6.6 times 10 to the minus 3. So So just copy it down exactly. 6.6 times 10 to the power of minus 3. And remember, it's wavelength, so the units of wavelength are meters, lowercase m, and underline it to show that that is the answer. In fact, my lowercase m's often look like uppercase m, so I'm just going to write that. Okay, just to make sure that the examiner absolutely cannot take a mark off me. So 6.6 times 10 to the minus 3.
Okay, let's start to look at ultrasound imaging. Now we know what ultrasounds are. So just read that text to me, please. Okay, so as I've already mentioned before, ultrasound can be used to build images of certain things that we cannot go inside. So such as a baby inside the womb, or some faults inside inside metal that we can't look inside the metal because that would break it. But we need to know that metal is strong before we build a bridge out of it, and there aren't any faults in the middle. So we can use ultrasound for that. So this is how it works. Read the text that's just appeared on the screen. So read from an ultrasound wave is emitted by a source. I'm going to just highlight a couple of words. So the one that says the wave travels through a substance, but when it meets a boundary between two mediums, remember that's different materials of different density. So when it meets materials of different density, they are partially reflected. What that means is, it's like in the reflection experiment. So when we put in the incident wave, the incident ray, and that is reflected out. Now, when we're used to reflections, if we look in a mirror, 100% of the light going in is reflected back out. But when we mean by partially reflected, it means that some of the ultrasound comes back, but some keeps going. So we can actually detect multiple different layers because we keep getting reflections every time the density changes. So here's an image of that. You can see that in that picture, the sound receiver is pushing out the red waves. Then they come in contact with the object, and then the waves are reflected back, and then they are picked up by the detector again. Here's an image that I drew. It's based on an exam question I've seen before. So we've got a detector in the ship, and you can see that a sound wave is sent down into the sea, and it hits the seabed because that will be a different density than the sea that it's going through. And then the wave is reflected, and it is detected again. So you can see that the initial spike on the graph at the bottom of there comes at 0.1 seconds. There's then some wobbles around, and that's because it might be, there might be some fish swimming in the way. So there are a couple of different densities. So you're going to keep getting little bits of sort of noise, little reflections sent back when it encounters anything of different density. But then at 0.20 seconds, there's a big spike back. So that indicates that's probably the seafloor. Okay, so by knowing the time that the wave was sent and it was received, means that we can start to build up an idea of how far away things are. So I've got 3 images that I've drawn for you here based on exam questions, but I couldn't quite find the exact exam questions I wanted, so I've drawn them out for you. The idea is that you are trying to understand what the oscilloscope traces is showing you. So that's the Aspire objective. So I'll give you the example in part A. So we would say that the first pulse is at 0.10 seconds. So that is where at the bottom on the graph, that's the first spike. That's the transmitted pulse. The second major pulse is at 0.20 seconds. So we call that the reflected pulse. So this would be the reflected ultrasound wave from the seabed. So that's my complete sentence. So what I want you to do is you don't need to write this down, but I'm going to give you 30 seconds just to figure out what the gaps would be in the two paragraphs below. So the one that starts with in example B, the transmitted pulse is at. So just figure out what the gaps would be. You've got 30 seconds to do that. Okay, let's check that we got that correct. So in example B, first pulse is at 5 milliseconds, second pulse is at 20 milliseconds, and the metal block at 30 milliseconds. In example C, the transmitted pulse is 0 milliseconds, and the layer of fat is observed at 2 milliseconds. Right, so what can we do with that information now that we can read these oscilloscopes? So we're going back to example A again. Well, what we can actually do is we can figure out the distance between the objects, which allows us to start to, if we know lots of distances, a computer can actually start to build up an image. So I was going to give you a little example. So here we've got a runner and we've got a wall. Now if I say that that runner takes 10 seconds to get to that wall, and if we say that they run at the average speed of running, which is 3 meters per second, we can work out how far away that wall is because we use this equation, speed equals distance divided by time. So we put in the speed is 3, distance stays, we don't know that yet, but the time is 10. So if we rearrange that equation, we get 3 multiplied by 10, which gives us 30 meters. So we know that that wall is 30 meters away. Now that works if we only know the time to the wall. But if you look at the picture in A, we actually know the time to the seabed and back. So it's a little bit different to this example. So let's say that we knew that the runner ran to the wall and back, and it took them 20 seconds. They're still running at 3 meters per second. We can still use our equation, but we just have to change it very slightly. And this is a common misconception that people make. So we do speed equals distance divided by time, but we need to divide our time by 2. So we have 3 equals the distance, which is unknown, 20 divided by 2, which is 10. So we end up with the same sum. We end up with 3 times 10, which still gives us 30 meters. So just a really important point. If you know the time to an object and back, you need to divide the time by 2. Okay, so your equation becomes speed equals distance divided by time divided by 2. So I'd like you to answer questions A to E in your books, please. Again, write in full sentences. So for A, you would say the instrument used to detect ultrasound is called A. I'll give you a clue. It starts with O. All right, you've got 3 minutes. Off you go. Okay, we're coming up to halfway through the time now. So, I've already given you a clue for A. It's a word that begins with O, ends in scope. It's something O, something scope. For B, why ultrasound's safer? Well, you need to use the word ionizing within your answer. So try and get the word ionizing within that answer. That's the key word there. Why? So when is an ultrasound reflected? I told you that on the last slide. It's to do with densities. Okay. Part D, that formula is on the same slide, so you can find that information within that slide if you're struggling. And then part E, you just have to summarize what I've just told you, but again, the information is on that slide. It's just about having it written down in your book so that you can refer to it later. You've got about 45 seconds left. Okay, that's the end of the time that we've got available for this one. So red pens again. Okay, in red pen again, you just need to check your answers. So once again, pause the video so that you can check your answers and be happy with them. I'm just going to leave it running for a couple of seconds before the video will automatically change, just to give you this time to hit the pause button. So this time we need to do some calculations. So the Aspire objective is to be able to calculate the distance to objects using oscilloscope traces. So the oscilloscope tracer, the thing that we just looked at, is that graph at the bottom of the image. So here's a model of how to do it. It looks quite confusing. So we've taken speed equals distance divided by time divided by 2. And we've just taken the information that we know from that question. So 1,600 meters is the speed. And the time, we've used the oscilloscope trace. So we've done the largest time, which is 0.20. That's when the pulse was reflected back. And the start time, which was 0.10, so that the time is 0.10 seconds. Then we divide that time by 2, and we end up with 1,600 equals distance divided by 0.05. So we rearrange by doing the opposite of what's happening to distance to both sides, so times by 0.05, and we end up with 1,600 times 0.05, and that would give you 80 meters. So I want you to have a go at some of these on your own. Now I'm going to give you some structure, some guided practice. So the idea in guided practice is that most of the question is done for you, but you still need to do it and you still need to follow along. It's just that you can refer back to the question. But there's each question I give you, there's one extra bit missing. So it just gets a little bit harder until the point where you're able to tackle the question independently and be confident doing these on your own. So how it's going to work is I'm going to click a video now that I've pre-recorded showing you how to use faded practice. I want you to work at the same time as the video, writing down exactly what's in the video as exactly it's set out on the video.
I want to show you what your book should look like when you're doing this faded practice, because this might be something that you haven't seen before. And it looks as though I'm just asking you to fill in the gaps, but I'm not. I'm asking you to work through, and I'm asking you to do the whole calculation. It's just that I've taken away one part each time. And the reason why is that that's the bit that you're going to be focusing on. And each time we'll take one extra step until the point where you're doing the whole calculation by yourself. So it's just providing some scaffolding just to help you with these activities. But it is important that you go through the whole calculations because they're going to guide you, and it's there to be your guide. So in your book, you would just have A. Now, I'm going to start a timer, and that timer will go as soon as I start writing, I want you to start writing with me as well, because we're doing the same thing. We're looking at A. We don't need to do anything with the model. The model's been done for us, so that's just a reference. But let's have a go at A. So we're going to start the timer now. So the first thing we're going to write down are the values that we know. So we can see that the speed is told to us, it's 3,000 meters per second. The other thing that we are told, or we can at least infer, is if you look at the oscilloscope graph, you can see that a transmitted pulse was sent out at 5 milliseconds, and the first one received back was 20 milliseconds, which indicates that that's the crack. So our time is the difference between those two. So the time is the difference between, so we start with a bigger number, so that's the 20, and we take away the 5. So our time was 15 milliseconds. Now we don't want to use milliseconds because our calculations won't work. We need to use standard units. So we are going to turn that into seconds. So milliseconds, you can see, to convert it to seconds, we divide by 1,000. So we do 15 divided by 1,000, and that's going to give us 0.015 seconds. Now what I like to do here is I like to cross out all the values that I've got for time that I'm not going to be using, because when I'm doing the calculation, I'm just very quickly looking back to see what numbers I need to substitute in. If I've got multiple numbers here, in the pressure of an exam, I might accidentally put the wrong one in. Right, now let's write down the formula that links speed, time, and we're trying to find distance. So we should know that speed equals distance divided by time. Speed equals distance divided by time. Now, if you look at part A, you can see that I've actually got time divided by 2. And remember, that's because on the oscilloscope, the ultrasound was sent out, it hit the crack, and then it came back. So that's the time, that 0.015 is actually the time there and back. So we have to divide it by 2 to find the time just to there, because we only want the distance to the object, not there and back. So let's substitute in our values now. So we've got 3,000 equals, distance is still unknown, divided by, following the operation down, time divided by 2. So our time is 0.015 divided by 2. Put it in bracket because we have to do that first. So it's a good idea now to simplify. So let's just simplify what we've got. So we've got 3,000, that remains unchanged. Distance, we still don't know. But this bit we've got a sum that we have to do here. So we're going to do that sum. Now, even though it tells you the answer on here, it's good practice to do it and use the guide to just make sure that your answer agrees. I've got 7.5 times 10 to the minus 3. If I look at that, 7.5 times 10 to the minus 3, so I know I'm doing the right thing. So 7.5 times 10 to the minus 3. Okay, now at this stage, we need to make D the subject. The distance needs to become the subject. So distance is going to be divided by this. So we're going to do the inverse operation to leave this on its own. So we're going to multiply by 7.5 times 10 to the minus 3. And if we do that to that side, we've got to do it to the other side. So multiplied by 7.5 times 10 to the minus 3. Okay, again, let's simplify this down. 3,000 times 7.5 times 10 to the minus 3 equals, and we've got distance divided by this times this. So this is going to cancel each other out, so that's going to leave us just with the distance. So this is the bit where we've not been told, so we have to do that, or you have to do that. I'm not going to do it for you, but you are told that the answer is in meters. So do that now. I'll give you a couple of seconds and put in what you think your answer is there. Okay, now we're going to go on to part B. So part B, speed equals distance divided by time divided by 2 again. So write down what we've got. So this time we've got a speed Remember, you're doing this with me, not watching this and then doing it yourself. Speed is 340 meters per second. Time. Now in this case, the pulse was sent out. It hit the end of the layer of fat, so it was partially reflected when it changed from fat to muscle tissue. So we got that first pulse back at 2 milliseconds. So we've got dead easy this one. Big number 2 minus the 0. So our time is 2 milliseconds. Okay. Now we don't want it in milliseconds, so what we're going to do is we're going to do 2, and remember, as we did before, but it's already shown for us, divided by 1,000. 2 divided by 1,000 equals, again, although it's shown for you, good practice, do it yourself, 2 divided by 1,000. 2 times 10 to the minus 3, does that agree? Yes, it does. 2 times 10 to the minus 3 seconds. Okay, cross out all of this so that your time is here. Substitute in. So the formula, speed, time, we're trying to find distance. Speed equals distance divided by time. Remember though that this is the pulse has been sent out and back, so it's time divided by 2. Let's substitute in. So 340 for speed equals distance is unknown divided by time divided by 2. So the time is 2 times 10 to the minus 3 divided by 2. Okay, let's simplify it down. So 340 equals distance divided by, and then let's do this, 2, just in case we were unsure, times 10 minus 3 divided by 2 equals 1 times 10 to the minus 3. Check it. Yep, that's what we've got on there. 1 times 10 to the minus 3. Okay, this is the bit where you have to do something. So you have to figure out what you need to do in order to make D the subject. I have shown you that it's the inverse of this is to multiply. So you're going to be multiplying this side by something, and you're going to be multiplying this side by something. And then when you've done that, your answer is going to be something multiplied by the 340, and that will give you the distance in meters. Okay, so just continue and solve that, please.
Okay, I'll give you another couple of seconds before we change the slide. Okay, let's move on to a little bit more removed. Red pen's out and just checking your answers to these sections. So in section A, the missing answer was 22.5 meters. If you got that, well done. In section B, you should have been multiplying both sides by 1 times 10 to the power 3, which would have meant that we ended up with that, which gives you 1.54 meters. Okay, I'm going to give you 5 minutes in order to try another 3 of these questions. If you can get to D, which is where you're doing it entirely on your own, and you feel totally comfortable with this, then you are absolutely at the point where I want you to be in this lesson, in that you can calculate the distance to an object using oscilloscope traces. Okay, 5 minutes. I'm going to be quiet now and let you focus and let you concentrate. Okay, we're coming up to halfway through the allotted time for this activity, so you should be on D at the moment. I'll give you one little clue for part D, because you should be doing this on your own. This is the hardest question I could find on ultrasound, just to really push you. In order to figure out the time, you have to look at how many spaces there are between the transmitted pulse and A, so how many little squares, and each of those little squares represents the time shown in the diagram. So multiply that by the number of little squares. That will give you the time, and that's my hint. Okay, that is the end of the time for this activity, so let's check our answers. Okay, grab your red pens and let's check our answers. So, on part C, we had speed equals distance divided by 2. So we had 1,600 equals distance, so the time was 0.4, and we divide that by 2. Now, if you do that, you get 1,600 equals distance divided by 0.2. Therefore, in order to rearrange this to make distance the subject, we've got to multiply both sides by 0.2, which ends up with 1600 times 0.2 equals 320 meters. That sounds sensible. Okay, for parts D and E, I'm going to show you a video of me modeling exactly how to do this.
First off, again, write down what we know. So we are told that the velocity, so the speed of the sound through steel is 6,000 meters per second. We are also told that the time can be found, and we're not given it. It's a little bit more tricky, this one. So each of those little squares between the transmitted pulse and where it's received again is 0.00005. That's 5 zeros and a 5. So the time, what we're going to do is we're going to count how many squares there are. So I go 1, 2, 3, 4, 5. There are 5 squares, and we're times 5 by the scale. So that's the 1 centimeter. So we've got 0.0000005 on there. Okay, and if we do that, that's going to give us our time. So if we just do that one now, so 5 times 0.12345 and then a 5 equals, press SD, 2.5 times 10 to the minus 5 seconds. Now don't worry about the fact that it says 1 centimeter represents that. The oscilloscope is just saying that on the oscilloscope 1 centimeter represents that, so that time is fine and we can use the meters. We don't need to convert. So we're being asked to find the distance, so we need the equation that links speed, distance and time, which is speed is equal to distance divided by time. I'm just trying to keep it on one line. So let's substitute our values. So 6,000 equals, distance is unknown, but time we do know. So it's 2.5 times 10 to the minus 5. But we need to remember that this is both ways. So it's to the receiver and back. So that means is that we've got to do this time divided by 2 in our formula. So we're going to do 2.5 times 10 to the minus 5 divided by 2 in our formula. Okay, let's simplify this so we've only got a maximum of two operations, because this is too much going on here. We could rearrange at this stage, but it's easier just to get it simple. So let's just do this. So 2.5 times 10 to the minus 5 divided by 2 is 1.25 times 10 to the minus 5. So we'll just replace that with the one number and we can keep everything else the same. So that's still 6,000 equals still the distance, and it's still divided by that. Okay, so at this stage we now need to rearrange because this needs to be our subject. So we've got to do the opposite of what's happening to the subject. So the subject is currently being divided by this number. So in order to leave on its own, we're going to multiply, because that's the opposite of the divide, by that number. So 1.25 times 10 to the minus 5 seconds. And we're going to do that to the other side as well. So times 1.25 times 10 to the minus 5. Okay, so let's now simplify this down. So 6,000 times by 1.25 times 10 to the minus 5 is equal to D, because this is a divide and a time, so they're going to cancel each other out. So let's do that sum. So 6,000 times 1.25 times 10 to the minus 5 equals 0.075. The light's a bit better. Equals 0.075, and this is the distance. So that's going to be in meters, lowercase m, and underline that. There you go. That's your answer to part D. Okay, part E. So in part E, I was trying to catch you out a little bit. Let's work our way through. So first off, we know the velocity. So the velocity of the sound through the water is 1600 meters per second. If you notice, that is lower than it was through the steel. That's because sound travels faster in more dense materials. So it travels a lot faster through the steel because the particles are a lot closer together than it does through the water, and it travels even slower through air, 320 meters per second through air. So the time. So we're told that it takes. Now, if you look at the arrow, it's only going to the seafloor. It sends a pulse, and it says it takes 0.25 seconds to travel from the submarine to the seafloor. That's different to this one because this one was the floor and back. So our time, we don't need to do anything with it here. So it's 0.25 seconds. And remember, we are trying to find the distance, which will be in meters. So write out our formula. Speed equals distance divided by time. It doesn't need to be time divided by 2 because it's only going one direction. So we've got 1600 equals distance is unknown divided by 0.25. Okay, now we are at a point where we need to rearrange because we want to find distance. So we do the inverse, which is multiply by 0.25. Same to the other side, multiply by 0.25. Make sure that the decimals are obvious for the whoever's looking at your paper. And now we're just going to simplify this down. So 1600 times by 0.25 equals, this is above and below, so therefore these are opposite operations, so they cancel out. So this is going to give us the distance. So 1600 times by 0.25 equals 400. Okay, so 400, and it's the distance, so it's in meters. And you need to think to yourself, is that sensible? 400 meters between a submarine and the bottom of the seafloor? Yeah, that sounds a sensible distance.
Okay, we're now going to summarize the key points from this lesson before going on and answering our Google quiz. This is the summary points from the lesson that we just had. So want you to write down the sentences and try and fill in the bits that are missing. There are 3 objects to fill in. I want you to pause the slide now and do that. Okay, now it's time to check your answers. Okay, now that we have learned about ultrasound and how it can be used for detection, your job is to complete all of the questions in the quiz that are attached to this Google form. So go through them really carefully, then hit the submit button and it will be sent to your teacher and automatically marked. All right, thank you for staying with me for this lesson. Hopefully we now understand a lot more about ultrasound and how it works than we did at the start.